Welcome everyone. Let's do some multivariable calculus. So today we are given a C1 function on a Euclidean space Rn, and for R positive we define phi r to be the average value of f over the ball of radius r centered at the origin. So this sign on the integral stands for the average that we will see in the proof. We want to find derivative of phi as a real valued function. Problems of this type come up a lot in PDE and in harmonic analysis. So let's look at some ideas here. So there is a big problem here, and that is you want to take derivative with respect to r, and r appears right on the domain on which you integrate. So we have been taught how to take derivatives of functions, but not taking derivatives of domains or shapes. So how on earth are we gonna deal with that? The answer is the beautiful change of variables formula, which in the undergraduate courses we call the U substitution. Okay. In the multidimensional case, it looks something like this. So we have a ball of radius r back here, and we have an integral over this ball. Can we instead do an integral on the ball of radius 1? Can I turn an integral over this region into an integral over that region? And that's exactly the U substitution in higher dimensions that we are talking about. So we need a map that maps this ball of unit radius to this ball of radius r. So you have x, and you want to have y equal some function psi of x. So here goes the function psi, which deforms the ball of radius 1 into the ball of radius r, and we want phi to be sufficiently nice, have a derivative and whatnot. The easiest way of doing that would be to have y being just r times x. So you can check that this is a one-to-one and onto map. It's basically just expanding or shrinking the ball of radius 1 into a ball of radius r. The expansion versus contraction depends on whether r is bigger than 1 or smaller than 1. So what we should know, what I believe you should know, is that to integrate a function over here in the target of psi, so if you want to integrate something over ball of radius 0r, instead you can do an integral over ball of radius 1, that is like the U substitution, and here my y is the change of variables, so this will be frx. So, and then you are gonna have dx, but of course there has to be some correction factor. So when you do U substitution, you also do du equals something dx, and that something is the Jacobian. And in the multidimensional case, so I need a bigger Jacobian formula, so I need more room, which is another indication that it's not too easy. So what happens is you take derivative of this psi, which becomes a n by n matrix, and then you take its determinant, and then you take absolute value. So this whole thing here is your Jacobian, and it's exactly the factor that is needed to make this equality happen. So this is one of the most useful and beautiful equalities, identities in integration theory. And this is true for Lebesgue integrals, also for Riemann integrals. Okay, so But what is this Jacobian in our special case? So Jacobian geometrically is how much area is expanded when you look at infinitesimal cubes. And in this case, it's not difficult to see that actually this Jacobian equals r to power n. I leave it as an exercise, but actually you can compute d phi precisely, and when you take the determinant, you will end up with this. So it's an easy exercise. I leave it there. So as a consequence, I have the following. The integral that I was interested in, which is integration over ball 0 r fy dy, is equal to integral over ball 0 1 of frx r to power n dx. And if I divide by volume of, so let omega n be volume of ball 0 1 in Rn. Then this is a constant, and it is known. The volume of ball of radius 0 r is just omega n r to power n, because in Rn the volume expands by power n. So this is just how much volumes of balls of radius r are, and as a result, my phi of r, which is average value of f over ball of 0 r, will be equal to, so when I divide by omega n Rn, the Rn here will go away, and I will end up with 1 over omega n, which is again just a constant. I have ball of 0 1 frx dx. Okay, so what did we achieve? Quite a lot, in fact. Remember, the problem was we were dealing with a domain that kept changing when r changed. But look at this side. Every integral will be on the same unit ball. The r, which was the problem, is now inside here. And we like it better than the integral over a varying region. And with this progress, actually the rest is quite smooth. All you need to do is believe that you can put the derivation inside the integral sign. Again, I won't get into that one because that's not the main point here. So my second claim, which is also quite easy, is that if you take derivative with respect to r of frx, so f, remember, is a function from Rn into r. It's a scalar valued function. So if you take derivative of this quantity with respect to r, this is actually gradient of f at rx dot x. So that is another chain rule. It's an easy multidimensional chain rule. So with this in mind, we can actually compute phi prime r. As I said, I won't justify why I can put in. So I'm looking at the last integral formula for phi r, and this is b0r, 0, 1, the whole point of making it 1. Now, derivative of the inside. So the only place where r appears is here. And when I take derivative, according to this formula, I'm only going to plug in gradient f computed at rx multiplied with x dx. Okay, this is quite explicit enough, but I want to actually go back to the ball of radius r that I started with. just so that I can compare phi prime to the original phi. And for that, I need to do the reverse of the change of variables that I just started with. Change of variables formula to get the following, that phi prime of r equals 1 over omega n. So here is the thing. So I want to do an integration. So everything should be expressed in Rx, because ultimately I want to replace my Rx with y. So that's why I want to have everything expressed in terms of Rx. So Rx, I don't want x, I want to put Rx here. R is just a constant. It comes out of this dot product, out of the integral. So I can pay for it up front here. And also, instead of doing dx, I want to do Rn dx. And again, I want to pay for that here. So I just multiplied by n plus 1 powers of r, and I divide by the same quantity for the reason that will be apparent in 1 second. So this will be 1 over omega n Rn. And this will be, now if I replace every Rx with y, and this is exactly the Jacobian times dx part, so I go back to integrating over 0 r of gradient f y, and this part is just dy. So the whole thing was putting r here instead of the one that was above there. So did I make things more complicated? Well, not really, because if you realize, this is again volume of this same ball here, and that means this is an average. So this is average of gradient of fy dot y dy. And that's the end of the story. I computed my phi prime of r in terms of, so phi r itself was an average integral, and now it's again expressed as an average integral. The interesting thing is that there is this 1 over r appearing here, and also, well, the inside, instead of integrating f, you integrate gradient f dot y. There can be many interesting corollaries of this equality. For instance, if gradient f is always perpendicular to the radial direction y, then the dot product is 0. You get phi prime 0, which means phi is constant. It doesn't matter what ball you take, the average of f will be the same. It comes up in dealing with solutions of Laplacian equation and whatnot. But anyway, this included many interesting tricks from multivariable calculus, an interesting application of the change of variables. So anyway, I hope you picked some tricks for future use. If you have any questions, please do comment. And of course, subscribe if you haven't, and spread the word. Thank you a lot, and see you in